So when we look at VSEPR and molecular shape, that's important to understand what a molecule actually looks like, but even more important is to help to understand what properties the molecule is likely to have. So we initially define covalent as either a polar or a non-polar bond. That is based upon whether the electrons are shared equally or unequally. And when they're shared unequally, we have a bond dipole, or sometimes called a dipole moment. Right here, HCl is a great example of that. Chlorine has a higher electronegativity than hydrogen. The electrons are pulled more closely to hydrogen, making that side partially negative, the other side partially positive. And in these pictures, the darker blue is a more electronegative area, or an area of higher electron density. For a simple molecule with just two atoms, the bond dipole, or the dipole moment of the bond, tells us about the molecule as a whole, because we just have that one bond. But when we have more than one bond, we have to look at how all of the dipoles within that kind of interact with one another. Those dipoles have magnitude, size, telling us how polar something is, but they also have direction. So we need to look at in what direction are they pointing? Are they pointing in the same direction, making the polarity increased, or are they pointing in opposite directions, canceling one another out? Or is there some in between there, some partial canceling or some partial combining? When we do that, we are looking at the overall molecular polarity, or the molecule dipole. The examples that we have right here are CO2, an element with a central atom and two things connected to it, each of which is a polar bond. Oxygen's more polar than carbon. Oxygen has a higher electronegativity than carbon. That's more correct than saying it's more polar. So the electrons are pulled one direction, but over here we also have a CO bond, so they're pulled the other direction. H2O is also two atoms to a central atom, but because of lone pairs, we don't have a linear shape, we have a bent shape. In this one, the bond dipole to the left is exactly equal and opposite to the bond dipole to the right. They would perfectly cancel one another out, and we no longer have an end which is negative and an end which is positive. So a magnet has a north and south pole. For a molecule to be polar, it has to have a positive and negative end, and that's not the case here. We don't have a red and a blue side. For water, there is a pull towards oxygen, which is somewhat inwards, and oxygen, which is inwards. So those cancel a little bit, but both of them are pulling kind of up with the way that it's drawn towards oxygen. So there is an overall pull of electrons upwards, with the hydrogens having less electron density down there, so a negative and positive end. Some key words we're thinking about in using this is the symmetry of the molecule. When all of the dipole moments, or when the molecule as a whole is totally symmetrical, all sides have the exact same thing, the exact same element with the exact same type of bond and no lone pairs, that symmetrical molecule tends to cancel all of the dipoles and make a non-polar molecule. When we have something asymmetrical, that could be because of different elements bonded to a central atom, or because of lone pairs on a central atom, that makes the molecule asymmetrical and therefore polar. So we've got some polar examples here. A diatomic molecule is really easy. We just look, is the bond polar or not? But here, NH3, kind of like water, has some lone pairs. So in one direction, there's electrons. Those are not canceled out by electrons in the other directions. So it is polar overall. The CH3Cl, the carbon has electrons being shared with all of the hydrogens fairly equally, but unequally with the chlorine. So we have a pull for electrons in one direction that isn't balanced in the other. For our nonpolar examples, very much like CO, we do have polar bonds, but they are pulled equally in all directions. So when we're trying to figure out if a molecule is polar or not, we have to start with a Lewis structure. That might be something that's given in a multiple choice or free response problem, or you may have to draw it. So in our examples, we start by drawing them. Then we look at the shape. we think about based upon the bonding regions and the electron regions, what would the three-dimensional shape be? Because looking at CO2 or H2O, it's possible to draw both of those in a straight line, but we would need to recognize on the H2O, those lone pairs make it bent in reality. That doesn't mean our Lewis structure has to be bent. It just means we need to remember that those lone pairs are important. We then need to know, is the bond polar or not? If we're sharing all electrons perfectly equally through our molecule, it doesn't really matter what the shape and the symmetry is, because electrons shared equally can't cause a dipole moment. So if we have polar bonds, we are then looking at the shape. Is the molecule symmetrical in all directions? Lone pairs, elements bonded to your central atom. And that's what would determine if there's a net dipole. Many times, if there's a lone pair on your central atom, it ends up being polar, but not always, depending on the shape. Many times, if there is different elements, so here like hydrogens and a carbon, two different things bonded to your central atom, that makes it polar, but not always. So with these practice, we go through those 4 steps, looking at the picture, connecting that to VSEPR, looking at electronegativities for bond polarity, but then lastly, looking for that symmetry and whether any dipoles that exist, any bond dipoles, either combine or cancel to make a molecule dipole or a net dipole moment.